Prepare to be amazed. Groundbreaking observations of black hole collisions are reshaping our understanding of the universe, offering unprecedented insights into Einstein's theory of relativity and the elusive nature of hypothetical particles. These discoveries, stemming from the international LIGO-Virgo-KAGRA collaboration, are not just scientific milestones, they're a testament to human ingenuity and our relentless quest to unravel the cosmos. Since the initial detection of gravitational waves 10 years ago, we've entered a new era of astronomical exploration. Hundreds of these ripples in spacetime, born from the cataclysmic mergers of neutron stars and black holes, have been detected. But the two most recent observations, from October and November 2024, are unlike anything we've seen before, potentially heralding a paradigm shift in our cosmic understanding. Let's dive into the specifics. The first event, labeled GW241011, occurred on October 11, 2024. It involved the collision of two black holes, with masses approximately 17 and 7 times that of our Sun, respectively. This event, which took place 700 million light-years away, was extraordinary due to the rapid spin of the heavier black hole before the merger. It was spinning at a staggering 75% of its theoretical maximum speed. The second event, GW241110, presented another unique scenario. Here, the black holes had masses of around 16 and 8 times the Sun's mass. The twist? The spin direction of the larger black hole. Instead of aligning with the orbital direction, as typically observed, it spun in the opposite direction, a first of its kind. And this is the part most people miss. These record-breaking events strongly suggest that the two larger black holes were already the products of earlier black hole mergers, making them second-generation black holes. This hints at the dynamic environments where these mergers occur, challenging our existing models. As Professor Stephen Fairhurst of Cardiff University, and spokesperson for the LIGO Scientific Collaboration, stated, GW241011 and GW241110 are among the most novel events among the several hundred that the LIGO-Virgo-KAGRA network has observed. He added that these events provide tantalizing evidence that these black holes were formed from previous black hole mergers. Gianluca Gem, spokesperson of the Virgo collaboration, emphasized the extraordinary capabilities of the global gravitational wave observatories. He noted that the unusual spin configurations observed not only challenge our understanding of black hole formation but also offer compelling evidence for hierarchical mergers in dense cosmic environments. They teach us that some black holes exist not just as isolated partners but likely as members of a dense and dynamic crowd. These discoveries underscore the importance of international collaboration in unveiling the most elusive phenomena in the universe. But here's where it gets controversial. The precision of these observations has allowed scientists to test both particle physics and general relativity. They've explored the potential effects of ultralight bosons, hypothetical particles that could explain dark matter, and have been able to exclude a wide range of possible masses based on the observations. In terms of general relativity, the team searched for deviations from Einstein's theory, but found a strong agreement between the theory and the observations. As Carl Johann Heister, assistant professor of astrophysics at the University of Nevada, Las Vegas, pointed out, this discovery also means that we're more sensitive than ever to any new physics that might lie beyond Einstein's theory. What do you think? Are you excited about these discoveries? Do you think we're on the cusp of a new era of understanding the universe? Share your thoughts in the comments below. And if you're curious, the full details of these findings are published in the Astrophysical Journal Letters.